I would like to welcome Mr. Daniel Pfarr, hello, for giving his presentation. Mr. Pfarr is a research assistant at the Institute of Building Construction at the Technical University of Dresden. He is working with Professor Engelmann, sitting over here also. After studying civil engineering, he began his doctorate and his research is now on possible applications of thin glass for future facades. So I think that is also the topic of today's presentation. Thin glass composite panels, the assessment of stiffness due to external bending load. Okay, the floor is yours.
Thank you very much. Yeah, thank you for the kind introduction, and thank you already to the audience for your patience here. Today, indeed, I would like to give you a short presentation about my PhD research, which is about thin glass composite elements, and in particular with additively manufactured core structure. And today I would like to focus on the assessment of the bending stiffness of these panels. And to jump into the topic, maybe with a short motivation why we should even use thin glass at all. And I think there are three major benefits we can profit from when we use thin glass. I think they are quite obvious. The first one is we can build very light structures, so very lightweight facades. Connected with that, we can save a lot of material investing in our facades. And the third is, like you can see in the picture, with the low geometric stiffness of the material or of the thin glass itself, we can open up new potential designs for our future facades. Of course, that comes with a lot of challenges, and some of them I would like to discuss maybe today. But that brings me to the agenda for the next, let's say, 15 minutes. I would like to get everybody to the same page with a short introduction and some theoretical background about the topic. After that, we dive into some analytical calculations about the bending stiffness and some experimental investigations, and maybe we can try to compare them. In the very end, there are some different parameters which are influencing the bending stiffness, which I would like to cover with the sensitivity study in this presentation. So let's get started with this rendering. It shows the thin glass composite panel, or the concept of the thin glass composite panel. So we take two very thin sheets of glass and we adhesively bond them to some kind of core structure. And in our case, it is a 3D printed, additive manufactured core structure made by a thermoplastic polymer. How is that made? So we set up a whole manufacturing process. So after a design phase, we can come to the production in our laboratory, and on the left-hand side you can see the additive manufacturing. In that case, we are using a quite simple honeycomb structure, but that is already very sufficient from a mechanical perspective. The next step is then the adhesive application. In our case, we use an hot melt adhesive. We apply it with the same robot which we are using for the 3D printing process. We melt the hot melt to a certain temperature around 200 degrees. Then we apply it. It's cooled down. We do it on the other side of the sandwich panel as well. And then we come to the third step, which is a kind of a lamination process. So we stack the thin glass on each side. It comes to an oven. We melt the polymer, the adhesive again, and then we hope that the bond is good enough. And if everything goes wrong, and if nothing goes wrong, we can achieve a thin glass composite panel. This is a picture from last year GlassTech. This is a curved composite panel made with exactly these steps which I have discussed already. Yes, and by doing that, we can achieve a very lightweight but still very stiff composite element. And now we have to think about, okay, if we want to go to the facade, we need certain steps to come around some challenges. And one is the assessment of the stiffness. And of course, we have different loads in a facade. We can, I think, divide them into external loads like wind or snow, for example. And on the other hand, we have a lot of internal load like the isochoric pressure, if we have an IGU, for example, or some thermomechanical aspects which we have to account for. For today, I would like to focus on the external loads, or to some external loads, and that brings me to the research question for the presentation, which is how can the bending stiffness of these thin glass composite elements be assessed, in that case for out-of-plane bending loads. So in a nutshell, what happens if we load the panel from outside? That brings me to some theoretical background, which is good to know. So if we would like to calculate the bending stiffness of this panel, we can do it in that manner. So we have a formula for the calculation that consists, like the composite, out of 3 different components. I don't have a laser here, right? No. So the upper one, I think it is highlighted in the blue, is accounting for the thin glass, and we have 2 parts here. One is accounting for the bending stiffness of the glass around its own center, or around its own neutral axis, and the second part, here marked as part 2, is the bending stiffness of the glass around the neutral axis of the whole composite, which is a major part because we have the distance of the whole core and adhesive adding up and distancing our glass from each other. The second part is in the same manner for the adhesive. We will see in a minute that it's not a huge part because it is has a very low stiffness. And the third part is then the bending stiffness of the core structure itself about its own axis. That was for the solid case on the one hand side, so it is our reference. And on the other side, we can try to account for the honeycomb structure we are using. So we need to incorporate something into the bending stiffness to account for the lower density of our core structure. In that case, the honeycomb structure, or the density of the honeycomb structure, is represented by the factor multiplying the width of the whole composite. Yes, the same we have to do for the shear stiffness, as we have already heard in the presentation before. It is not only bending stiffness, it is shear stiffness, which is important as well, especially for this soft interlayer we are using. So that is then the calculation of the shear stiffness, and in that case, that is why my question was in the presentation before. It is only the calculation from a tensile test, so coming from the Young's modulus and the Poisson ratio. So with that stiffness calculation, we can go one step further to the calculation of the bending deflection and the shear deflection. So that is our basic setup, which we are replicating then later on in the experimental investigation. So it is a 4-point bending setup, and now it's quite important to differentiate between the bending deflection and the shear deflection, representing the both stiffnesses what we have calculated before. These both are adding up to a total deflection, and that is something we can compare then with our experimental results. Some materials and geometric basics here. So we have on the one hand side our reference, which is a solid core of polymer. So let's say 100% density. And on the right hand side, it is the honeycomb structure which we are using. It is representing the specimen for the experimental setup with a width of 500 millimeters and a length of 1,500 millimeters. And in that case, our density is 10.8% for the core structure. We have some materials used, 3 different components. So we have the face, which is a thin glass, 1.1 millimeters thick. We have the adhesive, which is around 1 millimeter thick as well. In that case, it is an polypropylene-based hot melt, which has a stiffness of around 90 Newton per square millimeters. And the core with a stiffness of approximately 6,000 Newton per square millimeter, according to the data sheet. And we investigated this with 3 different core thicknesses, 14, 19, and 24 millimeters. And I don't want to overwhelm you with that table, so maybe I can guide you a little bit here. So what you can see in the upper part is the calculation of the bending stiffness and the shear stiffness for the solid assumption, so our reference. And on the lower part, it is the calculation of bending and shear stiffness for the honeycomb. And we have the total bending stiffness here in the very end, and we have these different parts, which I have already shown you before. And now it's quite interesting to look at the percentage of their contribution to the total bending stiffness. And in that solid case, we can see that the major part is covered from the thin glass related to the central axis of the whole composite, but there's also a decent part for the bending stiffness of the core itself, around 10 to 20%, depending on the thickness of the core. And if we look into the honeycomb, then we can see this amount of bending stiffness for the core is decreasing around 1 to let's say 3%, and so the major part is really covered from the face sheets. That is very well known as the sandwich effect. The shear stiffness as well, here in that case it's only one component, but comparing the solid against the honeycomb, so we have a huge difference in shear deflection, so we can expect in shear stiffness, so we can expect a higher amount of shear deflection, which we can look right now. So in that graph we have represented our 4-point bending test, only the half of it. On the left side it is the solid assumption, on the right hand the honeycomb assumption, and then we have our 3 colors representing the 3 different thicknesses which we have investigated, and then we see some dotted line and some dashed line. So the dashed line is the bending deflection, the dotted line, which is here almost 0, is the shear deflection, and then the total deflection, which is a solid line. And on the right hand side with the honeycomb assumption, we can already see that we increase the shear deflection, we increase the total deflection, and therefore we have to take into account the shear deflection of the composite panel, and that is only for this one example. By calculating the deflection of these panels, so on the right hand the diagram with the mid-span deflection, the total mid-span deflection, and on the left hand side that's the force we are applying in our 4-point bending test, and this graph we will later on compare with our experimental results as well. Where we come to right now, so that's the experimental investigation. So we have our 4-point bending setup on the left hand side, and on the right hand side just a picture from our laboratory where we have tested, and this is coming out with our results and already the comparison to our analytical model. We have the 3 diagrams representing the 3 different thicknesses, and on the left hand side we have ones with the triangle, that's the solid assumption, on with the circle, the honeycomb assumption, and then our experimental line for every 3 thicknesses, and we can then see if we can compare the honeycomb assumption with the experimental, that we have a certain area where we can see, okay, we have a fair estimation of the bending stiffness and of the deformation, but as soon as we have a deflection more than 10 millimeters, the deviation is just too high between analytical model and the experimental model. So I would say that's already a fair starting point, but still some room for improvement. Next, we have asked ourselves, okay, which parameter is actually influencing which part of the deflection? So we have 4 different parameters investigated. I would like to start with the core thickness. On the left-hand side, the diagram is showing you the mid-span deflection, the total mid-span deflection over the force. And on the right-hand side, we can see the differentiation between bending deformation and shear deformation. Again, in dotted and dashed line. And we have a relative shear proportion, which is interesting for us as this colored red line. And we can take out of these 2 diagrams, especially from the left one, that we have a significant influence on the total deflection between a core thickness of 10 up to 50 millimeters, that was expected. And on the right hand side, we can see that we have a very high influence on the bending stiffness and a very low influence of this parameter on the shear stiffness. So that was the first parameter. The second one is the variation of the Young's modulus of the core So we expected actually that, okay, the core, it depends really much on the material we are using and we are printing. But in that case, we have varied the Young's modulus between 1,000 to 10,000 Newton per square millimeter. And we can see there's almost no variation in the bending stiffness or in the deflection of the tests. So we can say that we have only a minimal influence on the total deflection. And looking on the right-hand side of the diagram, we can also say that we have a very low influence on the bending stiffness and no influence on the shear stiffness. The third parameter is the density. So of course we would like to achieve a very transparent module. So we would like to reduce the core density of the panel. And we have here varied between 0.5% up to 100%, and we can already see that we have a significant influence on the total deflection for core densities above 12.5 or below 12.5%, and we can see that we have a very low influence on the bending stiffness, but in that case a very high influence on the shear stiffness of the whole composite. The fourth and the last parameter we have investigated is the adhesive material stiffness. We have said, okay, we have adhesive which deforms quite a lot. So we have varied the Young's modulus between 1 and 2,000 Newton per square millimeter. And in that case, it was also quite interesting that we have a very significant influence on the total deflection when we have a stiffness below 100 Newton per square millimeter. And as soon as we keep this threshold above 100 Newton per square millimeter, then the deflection is not increasing that much, which we can see already here in the left-hand side of the picture. Yes, in that case, so we have no influence on the bending stiffness, but a very high influence on the shear stiffness. So to come to an end and have a short conclusion and summary. So I think we can say that the analytical calculation of the bending stiffness provides already a reasonable approximation of the experimental data. But of course, there is some space for improvements. For example, the nonlinear material or some geometrical effects, which we have not covered in the calculation. The influence of strain rate could be a very important one. The variability due to manufacturing quality, so because of the 3D print or the application of the adhesive could be play a role here, and the assessment of the core density, which is sometimes or can be quite complex if we are changing it from a honeycomb to a different one. And we have some design recommendations at the very end coming from our parameter study. So we can say that the core thickness is the dominant factor when we want to influence the bending stiffness of the composite. The core material stiffness has more or less a very minimal influence of the overall stiffness, which gives us a little bit of freedom in the choice of our material for the core. And the core density has a significant influence, but as long as we achieve a certain amount of core density, we can hold this threshold and limit the total deformation. And last but not least, the adhesive material, of course, is a very significant component. So at least we need to hold maybe 100 Newton per square millimeter, at least for this setup we have investigated, to ensure a certain stiffness, especially shear stiffness for the composite. And with that, I would like to end and thank you very much for the attention. And if there are any questions, of course, I think we can try to clarify them. Thank you very much.